Everyone talks about going to the stars like it's just an engineering problem. Build a big enough ship and you're done. But the moment you aim for Alpha Centauri, you start a stacked death race. Vacuum can knock you out in 15 seconds. High G burns can crush your organs. Your engine floods you with radiation. Dust hits your hull like invisible gunfire. And decades of isolation quietly shred your body, your mind, and your ship. In this video, we're going to ride that journey from launch to landing. And, at every stage, ask the only question that really matters. What kills you first? First problem, the vacuum. Space between planets is not just thin air, it is almost nothing. Pressure out there is around a tiny fraction of a pascal, while at sea level on Earth, you live at about 100,000 pascals, roughly 14.7 pounds per square inch. That is a drop of around 1 trillion times. Your body is used to that outside pressure pushing back on your skin and your lungs, and when it vanishes almost instantly, you're suddenly the high-pressure object in a near-zero pressure environment. That huge drop in pressure does something very specific to the water in your body. Liquids boil when their vapor pressure equals the surrounding pressure. Drop the external pressure low enough and water will boil at room temperature. So the thin films of liquid on your tongue, in your nose, on your eyes, in the moist parts of your mouth, start to boil away. Not because they are hot, but because the outside pressure is now so low that liquid water is no longer stable there. Your saliva foams, your tears try to turn into vapor, your skin begins to dry out extremely fast. This is simple phase change physics, not drama. So does that mean your whole body explodes like in bad sci-fi? No. Your skin, your fascia, all the connective tissue in your body is strong. It holds your blood and deeper fluids in. The pressure inside you does rise a bit as gases expand and dissolved gases come out of solution, so you puff up, but you do not burst like a balloon. You might swell to maybe 1.5 times your normal volume, your veins stand out, your skin stretches, but you stay in one piece. The weak point is not your skin, it is your lungs. When a cabin suddenly loses pressure, the air inside your lungs is still at close to earth pressure, and it wants to expand. If you clamp your mouth shut and hold your breath, you lock that high-pressure air inside a network of tiny, delicate sacs. Those sacs are so thin that oxygen and carbon dioxide can cross in fractions of a second, which also means they tear easily when they're forced to inflate too far. Think of them more like soap bubbles than like tires. The result of holding your breath in a rapid decompression is that those sacs rip. Air is forced into places it should never go, into the spaces around the lungs, and even into blood vessels. That can trigger massive internal damage in a fraction of a second. This is why every real space agency teaches the same rule. If pressure is dropping, you breathe out, you do not try to save the air in your chest. You sacrifice that last breath to save your lungs. If you get this wrong, the first thing that kills you is not vacuum in general, it is direct mechanical failure of your lung tissue. But even if you do this perfectly, even if your lungs survive the pressure change, you're still in trouble because the next killer is lack of oxygen to the brain, and that countdown is extremely short. Your brain uses a lot of oxygen, but it cannot store much. On Earth that is fine, your lungs and blood constantly resupply it. In vacuum there is nothing to breathe, and because the pressure is so low, there is no way for fresh oxygen to move from lungs into blood in a normal way. Whatever oxygen is already in your blood at the moment of exposure is all you get. Studies of rapid decompression and pilot training give a clear number here. You have around 10 to 15 seconds of useful consciousness. That means 10 to 15 seconds where you can move, think, react, do anything on purpose. After that, the oxygen level in your brain drops below what your neurons need, and your vision narrows, sound fades, and you black out. Around 30 seconds with no effective oxygen supply, brain cells start to die. So your personal story ends not in some long drawn-out struggle, but in less time than it takes to send a text message. At this point, people usually jump to temperature, and they say, "Space is freezing. You would just freeze instantly." That is not how heat works out there. On Earth, you cool down fast in cold air or cold water. because molecules around you steal your heat by contact and by moving past you. In vacuum, there is basically nothing touching you, so there is no air to conduct heat away and no wind to carry it off. Your body only loses heat by radiating it as infrared light. The same kind of heat a warm stove or a person gives off in a thermal camera. At normal body temperature, your body glows in infrared with the power of a few hundred watts, like a handful of bright light bulbs. That will slowly cool you, but not in seconds. It takes time for your core temperature to drop, and you do not stay conscious long enough to feel cold in the normal sense. The real twist is sunlight. Near Earth, the sun dumps around 1,360 watts of energy on every square meter facing it. If your bare skin faces that with no suit, you are being blasted with more energy than a typical kitchen hot plate, constantly. So now your thermal situation is very uneven. The sunlit side of your body heats up and burns. The dark side facing deep space radiates heat away and cools. You get strong temperature differences across your body, not an instant clean freeze. From a survival point of view, this detail barely matters, because lack of oxygen is already shutting your brain down while this is starting. Radiation from the sun does add another layer of damage. Our atmosphere filters out most of the dangerous ultraviolet and X-ray light, and Earth's magnetic field bends away a lot of charged particles. Without those, raw sunlight in space is much harsher. Your eyes are at special risk. They focus light, including ultraviolet, onto a small patch of tissue. Stare toward the sun with no visor or protection, and you can damage your retinas very quickly, on timescales of milliseconds to seconds. Your skin, unshielded, starts to take heavy ultraviolet damage in minutes. It is like the worst sunburn of your life compressed into a tiny window of time. Add all of this up and the order of events is clear. First, you step into vacuum, moisture on your body starts boiling, you begin to swell. If you hold your breath, your lungs tear, and that alone can be fatal in moments. Even if you do not, you lose consciousness in about 10 to 15 seconds because your brain runs out of oxygen. After that, while you're unconscious, your tissues continue to dry, gas bubbles form in your blood. Your organs take damage from swelling and lack of circulation. Radiation and uneven heating keep adding injury, but those are finishing blows, not the first strike. There is a tiny rescue window. If someone drags you back into a pressurized, oxygen-rich environment in under 15 seconds or so, and your lungs have not ruptured, you might recover with limited damage. By 60 to 90 seconds, serious brain injury is almost guaranteed. Past that, your heart may have stopped, your blood chemistry is wrecked, and bringing you back is extremely unlikely. So, to just survive empty space for more than a handful of seconds, you absolutely need a sealed, pressurized, temperature-controlled shell around you, with air at close to 1 atmosphere, around 100 kilopascals, and proper shielding from sunlight and radiation. Without that, your trip to a star 4 and a bit light years away ends a few meters outside the airlock. But once you do have that protective shell, once you are sealed into a starship that keeps a tiny bubble of Earth conditions around your body, a new problem appears, a bigger one. To actually make progress toward Alpha Centauri in anything like a human lifetime, that ship has to accelerate very hard for a very long time, and that turns simple acceleration, the same thing you feel in a car or a roller coaster, into the next thing that can kill you first. You solve the vacuum problem by staying inside the ship. Now a new question appears, and this one is worse. How do you move that ship fast enough that you reach Alpha Centauri before you die of old age, without the acceleration itself destroying your body? First, you need to know what fast enough even means. Alpha Centauri is about 4.37 light years away. In distance, that is roughly 4.1 times 10 to the 13 kilometers, or about 25.7 trillion miles. If your ship somehow cruises at 10% of the speed of light, around 30,000 kilometers per second, about 19 million miles per hour, the trip still takes around 44 years of coasting. That is 44 years not counting the time to speed up and slow down at the start and end. So how hard do you need to push to get to that 10% light speed? If you accelerate at about 1g, the same acceleration as gravity at Earth's surface, about 9.8 meters per second every second, You reach 0.1 C in a bit over a third of a year, around 4 months of continuous thrust. For a human body, 1 G feels normal, like standing on the ground. You can live with that. Eat, sleep, walk around, all fine. Now change one design choice, push at 5G instead, 5 times Earth gravity. Now you reach that speed about 5 times faster in less than a month, but the load on your body is also 5 times higher. So the first hard limit is simple. How much continuous acceleration can your body take before it fails? The faster you want to go and the quicker you want to get there, the more you press up against that limit. Think about how different G levels actually feel. At 1 G, nothing sacral, that is just your normal weight. Your 70 kilogram body, about 155 pounds, feels like 70 kilograms. At 2 G, your apparent weight doubles. Now your body feels like 140 kilograms, around 310 pounds. Standing up, lifting your arms, even breathing starts to take more effort. At 3 G, that same person is effectively 210 kilograms, about 465 pounds. Your chest is heavier, your face pulls back, your heart has to work much harder to push blood up to your brain. Healthy, trained people can tolerate short bursts of 3G or 4G in the right direction, especially if they are lying on their back so the force is spread across their whole body. Fighter pilots can reach 9G in sharp turns, but only for seconds, with pressure suits that literally squeeze their legs and abdomen to keep blood from draining away from the brain. They also train for years to handle this, and even then, they often grey out or black out. For a starship, sustained 5G or 6G for minutes to hours, let alone days, is a different story. Your cardiovascular system is not built for that. Your heart struggles to keep enough blood in the upper part of your body, your blood pressure swings, small vessels in your eyes and brain can rupture, and organs shift under their own weight. Without extreme support, you are looking at loss of consciousness, organ damage and death, not over months, but potentially in minutes. So what is actually happening to you physically when the ship accelerates hard? The basic rule is, the force on you is your mass times the acceleration. You feel that as effective weight. If you are 70 kilograms and the ship is pulling 10 G, the acceleration is about 98 meters per second every second. So your effective weight becomes around 700 kilograms over 1,500 pounds. That load is pressing you into your seat or into the floor. Your ribcage and spine were designed for 1 G, with some margin for running, jumping, lifting. Under 10 times that, the structure is overloaded. Spinal discs compress, vertebrae are squeezed together, and tiny cracks can start in bone and cartilage. Soft tissues get pulled and stretched. Blood is heavy too. Under high G, it slams into the back of your body, pooling in your legs and lower torso if the acceleration is head to toe, or crushing your chest if the direction is different. Tiny capillaries in your eyes can burst, leading to vision problems. In extreme cases, your heart simply cannot generate enough pressure to overcome the extra weight of the blood it has to lift, and circulation to the brain stops. You can flip the ship and orient the seat so that acceleration pushes you back into the chair, from chest to back, not head to foot. That spreads the load a bit better, but the core issue remains. High, sustained G levels turn your own mass into a crushing force on your body. Here is the trap, and there is no way around it. If you want the trip to feel short in ship time, you have 2 options. You can accelerate harder, meaning more G, so you reach cruise speed faster. That shrinks the time you spend speeding up, but it drives your body closer to its structural limits. Or you can keep acceleration low and gentle, maybe 1 G or less, which is much safer for humans, but then you need to burn the engines for longer to reach the same speed. That means more propellant, bigger engines, longer exposure to every other risk, like radiation, mechanical failure and life support breakdown. There is no free choice here. Make the ship gentle on humans, and it must be bigger and more complex, which opens the door for other failures. Make the ship leaner and more aggressive, and the thing threatening to kill you first might just be the acceleration profile you chose at the drawing board. Now add one more layer that is easy to overlook at low speeds, but becomes brutal as you start talking about fractions of light speed. Once you go past maybe 20% of light speed, around 60,000 kilometers per second, 37 million miles per hour, the rules of relativity start to matter. Your speed is no longer a simple distance over time story. The energy in your motion grows very fast as you get closer to light speed. In simple terms, the faster you go, the more and more energy each tiny extra bit of speed costs you. At everyday speeds, if you double your speed, the kinetic energy goes up by a factor of 4. As you approach light speed, the factor gets even worse because your effective inertia increases. That means the engines need to pour in huge amounts of energy just to add a small extra percentage of light speed to the ship. All of that energy is stored in your motion. From your point of view inside the ship, you just feel a steady 1g or 2g. But in absolute terms, the kinetic energy of the ship plus crew reaches numbers comparable to nuclear arsenals or asteroid impacts. If you ever need to stop more quickly from those speeds, you're not just slowing down, you're asking the ship and your body to handle the same gigantic energy flow in reverse. Any emergency braking maneuver would slam you with high G in the opposite direction. If the ship's structure or your own tissues cannot take that, you get torn apart or pulped long before you reach safety. So the paradox is clear. To cross interstellar space fast enough for humans to see the destination in one lifetime, you need high speeds. High speeds demand long periods of acceleration and deceleration. Long periods of acceleration and deceleration push the limits of what the human body can safely endure in terms of G forces. Turn the G down to keep people alive, and the trip time stretches into something close to a full human lifespan, which makes every other slow, quiet killer on the ship more likely to catch you first. And even if you find the perfect balance, say a constant 1G profile that slowly flips in the middle so you accelerate halfway, then decelerate halfway, you now face a new problem. Keeping up that thrust for months or years means your engines must run almost constantly at power levels beyond anything used on Earth, and that turns your own propulsion system into the next serious candidate for the thing that kills you first. You fix the G-force problem by keeping acceleration gentle. Now a new problem steps up and it sits right behind you. Your engine is basically a small artificial stub bolted to the back of your ship, and the first thing it threatens to kill is you. To get a 1 million kilogram ship about 1,000 tons up to 10% of light speed, you need an insane amount of energy, on the order of 10 to the 21 joules of kinetic energy. In plain language, that is roughly 1 million times more than what a big modern city uses in electricity in a whole year. You are not spreading that out over a continent. You are pushing that through a machine the size of a skyscraper, strapped to a vehicle that also has to keep humans comfortable at room temperature. Even if your drive is very advanced and very efficient, you still have to generate power at levels that beat major power plants on Earth, and you have to do it continuously for months. On a map, that just looks like a long straight line of thrust. In reality, it is a continuous blast furnace attached to your habitat. So what happens to all the energy that does not go into pushing the ship forward? No engine is perfect. Say your miracle drive is 50% efficient, which is already much better than most real engines we have today. That means half the energy you pour into the engine goes into accelerating the ship, and the other half turns into waste heat in the structure, in the reactor, in the exhaust system, in the wiring, everywhere. That extra energy has to go somewhere, or the ship heats up. You cannot open a window and vent hot air. There is no air outside. The only way to get rid of heat in space is by radiation, by glowing in infrared the same way a hot stove glows. To dump gigawatts of waste heat, you need radiators that are huge, thousands to tens of thousands of square meters, spread out like giant black wings, running at high temperatures hundreds of degrees above freezing. Those panels are thin, fragile, and absolutely critical. If you lose some of that radiator area, maybe from a micrometeoroid strike, a pump failure, or a control glitch, the waste heat backs up. Your comfortable 20 degrees Celsius, about 68 degrees Fahrenheit, starts creeping up. First 30 degrees, 86 Fahrenheit, then 40, 104, then into the range of 47 to 77 degrees Celsius, 116 to 171 Fahrenheit. In that range, you're not just sweaty, you're in real danger. Your body's cooling systems, sweating and blood flow, cannot keep up. Your core temperature climbs and you hit heat exhaustion and then heat stroke. Inside a starship, this does not take weeks. With gigawatts of waste heat and nowhere to send it, the air and metal around you heat quickly. Life support systems also run hotter and less efficiently. Electronics start to fail, plastics soften, lubricants break down. Heat becomes a chain reaction, and long before you see the new star up close, you can be cooked by your own engine. That is just the thermal side. The other side of the engine problem is radiation. High-performance drives would almost certainly be nuclear in some form. Fusion reactors, antimatter annihilation, or very high-power nuclear electric systems. All of those spew out ionizing radiation, things like fast neutrons, high-energy gamma rays and charged particles. Neutrons at these energies can travel deep into solid matter, tens of centimeters into dense metals, much further into lighter materials. Gamma rays pass through meters of water or rock before they are cut down to safe levels, so you wrap the reactor and the engine in shielding, maybe thick blocks of water, hydrogen-rich plastics, or even layers of metal. You aim the worst of the radiation out the back, away from the crew, but if your calculations are off by a factor of 10, or your shielding erodes over time, or a piece is misaligned, the crew compartment can start taking doses far above what astronauts see today. Right now, for people on the International Space Station, we already worry about total yearly doses around 1/10 of a sievert, because even that small number, over time, increases cancer risk. A few sieverts delivered in a short period, maybe hours to days, push you into acute radiation sickness. Nausea, vomiting, blood cell loss, organ damage. At around 4 to 5 sieverts without perfect medical care, half the people exposed will die. Your engine can deliver those levels very easily if shielding fails, and the main exhaust itself is a hazard, not just to other ships but to your own structure. At relativistic exhaust speeds, the plume is not just hot gas. It is a beam of extremely fast particles, more like the output of a particle accelerator than like the exhaust of a rocket you see on a launch pad. Any part of the ship, an antenna, a sensor boom, a radiator edge, that strays into that beam gets hammered by those particles. At those energies, solid material behaves like it is being hit by a constant stream of tiny bullets. Atoms are knocked out of place, chains of molecules break, surfaces erode. In engineering terms, your exhaust can drill through structure and hardware. A small misalignment in the gimbals that steer the engines, a guidance error that rotates the ship a few degrees the wrong way, and you can cut your own systems apart with your thrust. Destroy the wrong radiator manifold or power bus that way, and you lose heat rejection or power distribution, and all the other dangers, like overheating and life support failure, follow right behind. Here is the hard twist. Malseu. The engine is not something you can just run occasionally and then switch off for safety. Continuous low-G acceleration, maybe around 1G, solves a lot of problems. It gives you artificial gravity without a spinning habitat, so your bones and muscles stay healthy. It shortens trip time, so you spend less of your life under radiation and isolation. But continuous thrust means the reactor is on all the time, the exhaust is firing all the time, and the waste heat is flowing all the time. So the thing that makes your voyage more comfortable day to day, low-G pushing forever, also keeps you one failure away from disaster. A stuck valve in the cooling loop, a crack in a radiator panel, a control glitch in the magnetic fields that steer the exhaust. Any of these can turn routine thrust into lethal heating or lethal radiation. You are depending on a machine that must run near perfect for years, maybe decades, with power levels greater than city-scale power grids in vacuum under radiation while being shaken by its own thrust. If anything in that chain fails in the wrong way, the first big killer on the road to Alpha Centauri is not space itself. It is the star you built and chained to the back of your home. But say you somehow get that under control, your engine runs smoothly, your shielding works, your radiators hold and you cruise at a steady 1G as if you were standing on Earth. That solves the acceleration and gravity problem, at least for as long as the drive lasts. What happens if anything forces you to shut that thrust off? Or if your design starts with long coasting phases at weightlessness, and your body has to live for years in almost zero gravity, with no engine to fake a floor under your feet? Turn the engine off and a new problem appears right away. Your own body starts to come apart in weightlessness, quietly, piece by piece, even if everything else on the ship is working perfectly. Microgravity sounds gentle, you float, you drift, there is no impact, no crash, no obvious trauma. But your body evolved to fight Earth's gravity, about 9.8 meters per second squared, 1 G every second of your life. Take that constant pull away for months or years, and the systems that depend on it begin to shut down. The first big target is your skeleton. On the International Space Station, astronauts in microgravity lose about 1 to 2% of bone density every month in the bones that normally carry weight: hips, thighs, lower spine. That is with strict exercise routines and careful nutrition. Stretch that over a 2-year Mars mission without aggressive countermeasures, and you are talking about 24 to 48% loss in those areas. Almost half of the supporting structure gone. Now extend that logic to a 40-year cruise to Alpha Centauri, with long coasting phases at nearly zero gravity. Even if you slow the loss with exercise and medicine, the trend is clear: calcium leaves your bones and enters your bloodstream, vertebrae compress, and the internal scaffolding that holds you upright weakens. Instead of being like steel rebar in concrete, your bones start to behave more like brittle chalk. Why does that matter before you reach another planet? Because fractures do not wait for a landing. Simple tasks, bracing yourself in a collision with a wall, catching a floating tool, even a minor fall if you have spin gravity part of the time, can snap a wrist, a rib, or a hip. A broken bone in a fully equipped hospital on Earth is bad but manageable. Broken hip on a starship with limited surgery options can mean you never move properly again, you lose independence, and you become a burden on the rest of the crew. In an emergency, when everyone has to haul equipment, close a hatch, or get to a shelter in seconds, that can cost lives. If your bones are melting away on the inside, what are your muscles doing during all this time, with no weight to lift? In microgravity, your big leg muscles, your back muscles, all the tissue you use to stand, walk, and keep posture, get the message: we are not needed. Muscle cells adapt quickly. Without the constant small signals from gravity, they shrink. On the ISS, even with over 2 hours of hard exercise every day using resistance machines and treadmills, astronauts return noticeably weaker, and they need weeks or months of rehab to get back to normal strength. On a starship, you cannot assume perfect training sessions every single day for decades. Machines break, spare parts run out, people get sick, they get tired of the routine. A few months of missed exercise here and there, and your quads, calves, and core muscles lose size and power. Now think about a fire in a module, a sudden small depressurization, or a leak in a cooling loop. You may have to drag a 100-kilogram tank, about 220 pounds, close a heavy manual valve, or wrestle a stuck hatch quickly under stress. If your muscles have shrunk, you might not be able to move that mass fast enough or at all. You can be fully trained, fully aware of the danger, and physically unable to do what you need to survive. That is how microgravity kills indirectly, not with one big hit, but by making you too weak to respond when something else goes wrong. Even if you somehow keep up the exercise and keep muscles and bones just strong enough, microgravity still rewires your body in another way, through your fluids. On Earth, gravity pulls blood and other fluids down toward your legs. Your cardiovascular system compensates with valves and pressure changes. In microgravity, that gradient vanishes. Blood and other fluids shift upward into your chest, neck, and head. Astronauts report puffy faces, thinned legs, stuffed noses. It looks like a mild cold, but inside the pressure around the brain and eyes is different. This constant headward fluid shift is linked to a condition called spaceflight-associated neuroocular syndrome, or SANS. Over time, the increased pressure around the optic nerve and the back of the eye can flatten parts of the eyeball and change vision. Some astronauts come back from long missions with permanent changes in eyesight, needing new glasses, sometimes with damage that does not fully reverse. On an interstellar mission lasting decades, this is not a minor annoyance. It can mean that by the time you're halfway to Alpha Centauri, your vision has degraded significantly. Reading fine text on screens, spotting a tiny crack, judging distances when working on equipment, all get harder. In a cockpit or control room full of complex displays, that can lead to mistakes. You do not need total blindness for this to be dangerous, just enough distortion that you misread one gauge at the wrong moment. While your eyes are slowly being affected, your heart is learning a dangerous new habit. It is learning to be lazy. On Earth, your heart works against gravity, especially when you stand up. It has to pump blood from your chest up to your brain while gravity is pulling that blood down. Move to microgravity, and that extra load disappears. Your heart does not need to be as strong to push blood around, so like any other muscle underused, it weakens and shrinks a bit. Your whole circulatory system starts to adjust to the easier job. This becomes a serious problem the moment you reintroduce any kind of gravity, either by spinning the ship to create artificial gravity, using thrust to give you 1G for a while, or landing on a planet. Now your body is back in a world where blood wants to run down to your legs again, but your heart and vessels are out of practice. Stand up too fast and blood drains from your brain, you feel lightheaded, and you can black out. This is called orthostatic intolerance. On a spaceship, that is not just uncomfortable, it is deadly. Picture needing to sprint from your bunk to a control station because of an alarm. You stand up, take 2 steps and pass out because your system cannot handle the sudden gravity load. You hit a bulkhead, maybe crack your skull, and you are also not at your post when the ship needs you. Even if you are conscious, a weaker heart and reconditioned vessels mean you tire quickly, your reaction time slows, and your margin for dealing with emergencies shrinks. Now layer one more slow, quiet effect on top of all this physical change, the way microgravity and an artificial environment mess with your sleep and your internal clock. Your brain runs on cycles roughly 24 hours long, tied to light and dark, called circadian rhythms. On Earth, sunrise and sunset plus regular social schedules lock those rhythms in. In orbit, astronauts circle Earth every 90 minutes, seeing many sunrises and sunsets per day, and they rely on strict lighting schedules inside the station to keep their internal clocks stable. On a starship, there is no natural sunrise at all, only lighting panels and timers. If those systems are not designed and managed perfectly, or if mission demands force people to work strange shifts, your internal clock drifts. You go to sleep when your body wants to be awake, you wake up when your brain wants to be in deep sleep. Over days and weeks, that leads to chronic sleep debt, the same kind of constant tiredness you see in shift workers or people with jet lag, but stretched to months and years. Chronic poor sleep does not just make you yawn. It reduces attention, slows reaction time, and hurts memory and decision-making. On Earth, that might mean a mistake in an email or a missed exit on a highway. On a starship, it can mean forgetting one item in a checklist, missing one valve position, entering one wrong digit in a course correction, or overlooking one small warning light about a slow leak. Tie that back to everything else: weakened muscles, fragile bones, altered vision, a reconditioned heart. Microgravity is not just making you feel floaty and light, it is quietly pushing every system toward failure. When another threat shows up, radiation, an engine issue, a dust impact, a life support glitch, the difference between we fix it and we all die may come down to a few seconds of reaction time, a single correct movement, one clear line on a display. Microgravity cuts into all of those. So even if you keep the vacuum outside, keep the engine under control, and keep the G-forces reasonable, just turning off gravity for years gives space another way to kill you before you ever see another star up close. And all of this damage is happening while you are still inside the relative safety of our own solar system, near the Sun, under the protection of its magnetic bubble. Once you head outward, beyond Earth's shield and then beyond the heliosphere itself, another, more direct threat starts to rise. The radiation from the Sun and from deep space that your ship has to face with no planetary protection at all. You left Earth's gravity behind, but you did not leave its real protection behind. Now the sun that kept you alive your whole life turns into a source of radiation that can hit you directly, and it does not care that you are just passing through on the way to Alpha Centauri. Start with the thing that is always there, even on a quiet day, the solar wind. The space around the sun looks empty, so how can something that thin matter to a starship? The sun is constantly blowing out a stream of charged particles, mostly protons and electrons, at speeds of about 400 to 800 kilometers per second, that is roughly 250,000 to 500,000 miles per hour. At Earth's distance, one astronomical unit, that wind has a density of just a few particles in every cubic centimetre, way less than the best vacuum chambers on Earth. That sounds like nothing, but your ship's surface is big and your mission time is long. Every square metre of your hull is being hit by these particles non-stop, second after second, year after year. Each impact knocks atoms out of place in coatings, slowly erodes exposed surfaces, and builds up electrical charge on insulating materials. Over time, that charging can trigger sudden discharges, like tiny lightning bolts inside electronics, which can flip bits in memory, upset sensors, and slowly degrade wiring and connectors. Thin foils, optical filters, solar arrays, all take damage from this constant particle flow. The solar wind is not going to kill you in an hour, but over years it quietly eats your hardware, and that sets you up for failures later, when you can least afford them. If the background wind can already cause trouble, what happens when the sun stops being quiet and throws a real tantrum in your direction? Sometimes the sun releases huge bursts of energy and particles, solar flares and coronal mass ejections. During those events, the particle flux can jump to thousands of times the normal level. On Earth, we have seen the side effects, the 1859 Carrington event that lit up telegraph lines, or the 1989 storm that knocked out power in Quebec. Those were with Earth's atmosphere and magnetic field still blocking most of the energy. Out in space, with no thick atmosphere and no global magnetic bubble, a big flare or proton storm can push a massive dose of radiation straight into your ship. Unshielded, an astronaut could absorb several sieverts over just a few hours. For context, around 1 to 2 sieverts in a short time is enough to start acute radiation sickness, nausea, fatigue, lowered immune function. Around 4 to 5 sieverts, without very high-level medical care, about half the people exposed will die. The sun can deliver that dose as just one bad day if you're unlucky with timing and direction. On low Earth orbit missions, astronauts survive these events because something else is taking the hit for them: Earth's magnetic field. That magnetic field acts like a giant invisible umbrella. It bends a lot of charged solar particles away, and it traps some in radiation belts that spacecraft can avoid or cross quickly. That is why being 400 kilometers up on the ISS, about 250 miles, is still manageable. You're riding just inside the shield. The moment your interstellar ship leaves that magnetosphere and heads out on a direct line to Alpha Centauri, that umbrella closes. Now you face the solar wind and solar storms directly. Unless you build your own magnetic shield on board, generating fields of many Teslas across tens of meters, which is far beyond what we routinely do now, you are stuck with passive shielding, layers of mass, and clever layout. You put crew cabins deep inside the ship behind fuel tanks, water tanks, and cargo, and you hope that's enough to slow and block the worst of the particles. But for the biggest flares, hope is not a plan. So you need something more focused, and that is where the idea of a storm shelter comes in. If you know a major solar proton event is on the way, you can move the crew into a small room that has extra shielding around it, usually made from materials that are already valuable on the ship, like water or food supplies. Water is good at stopping protons and moderating neutrons, so you stack tanks around a tight core, and you wait there while the worst of the storm passes. The catch is timing. On a mission like this, you depend on solar monitoring either from your own instruments or from probes closer to the sun to give you hours of warning. If communication delays, sensor failures, or just bad geometry mean you miss that alert, you could be sitting in normal living areas when the storm hits full strength. Then every extra minute it takes to get people into the shelter is more dose to their bodies. A single large event can give a whole crew what would normally be considered a lifetime career radiation dose in just one afternoon. All of this risk is not just space is dangerous, it also comes straight from how you choose your path out of the solar system. Most missions tend to hug the ecliptic plane, the flat disk where most of the planets orbit, because that is where orbital mechanics is easiest and where gravity assists and other maneuvers are convenient. That plane is also roughly where the sun's activity is strongest. Stay near it and you face more flares, more coronal mass ejections and more interaction with the denser parts of the solar wind. You can design a trajectory that climbs above or below that plane to reduce the average exposure, but that usually costs more energy, more propellant, more time, or more complex engine burns. Cut corners on that to save fuel, or cut corners on shelter mass to save weight, and you are betting the whole mission on getting lucky with solar weather for years. Get that bet wrong, and the first thing that kills you on the road to Alpha Centauri is not deep space and not cosmic rays, not alien dust. It is a pulse of radiation from the same star that used to warm your face back on Earth. And that is still only the radiation story while you are inside the sun's larger protective bubble. Past the heliosphere, beyond the reach of the solar wind, the background level of high-energy particles from the galaxy itself rises, and you leave the sun's anger behind only to enter a much colder but even more relentless ocean of cosmic rays. You leave the sun behind, the flares drop off, and it feels like things should get calmer. But the opposite happens. Once you cross the boundary of the solar system's protective bubble, the background radiation steps up, and it never lets you rest. The sun's wind does more than just blow past planets. It inflates a huge bubble in the surrounding interstellar gas, called the heliosphere. This bubble stretches tens to over 100 astronomical units from the Sun, so well past Pluto's orbit. The Voyager 1 and Voyager 2 probes cross the edge, the heliopause, at around 120 astronomical units. Inside this bubble, the flowing solar wind and its magnetic field deflect a significant part of the high-energy particles coming in from the galaxy. It does not block everything, but it trims the worst of the flux. Outside that boundary, there is no more help from the sun's field. The average intensity of fast protons, helium nuclei, and heavier ions goes up, and it stays up for the rest of the journey. So what are these particles actually like, and why are they harder to deal with than the sun's own radiation? Galactic cosmic rays are mostly individual protons flying at huge speeds, plus a smaller fraction of helium and heavier nuclei. Their energies range from a few 100 million electron volts to many billions of electron volts per particle. You can think of the higher energy ones as packing the energy of a thrown baseball into something with the mass of a single proton or helium nucleus. They move so fast that normal shielding ideas from hospitals and nuclear plants stop working well. Their flux seems tiny on paper, just a few particles per square centimetre per second, but that per square centimetre is important. Your body has thousands of square centimetres of surface area. Every square centimetre is being hit every second, and your exposure clock runs not for hours or days, but for years. The dose builds up. For a Mars mission, current estimates say a crew might collect around 0.6 to 1 sievert in total from cosmic rays and solar events combined, round trip. That already pushes against our accepted lifetime limits, because it means a several % higher chance of fatal cancer later in life. Stretch the mission to an interstellar cruise, 10 to 20 times longer exposure, and you're looking at several sieverts over a career even if you get lucky with solar storms. That is not an instant kill like a big flare, but it is more than enough to drive up cancer rates, damage the heart and blood vessels, and hurt the brain over time. Why not just add thicker walls? For lower energy radiation, doubling the shielding can dramatically cut the dose. For these very fast particles, things get ugly. A high-energy proton or heavy ion can punch through tens of centimetres of aluminum, the kind of metal that forms spacecraft hulls. To seriously slow them down, you would need meters of material, and every extra centimetre is more mass you have to accelerate to 10% or 20% of light speed. The rocket math punishes you for trying. And there is a second catch. When one of these high-energy ions hits shielding, it does not just stop harmlessly. It smashes into atoms in the shield and creates a shower of secondary particles, like a small nuclear reaction. You get pions, muons, neutrons, and lighter nuclei, all flying out in different directions. The primary particle was a single track, After the collision, you get a spray. Some of those secondaries then reach the crew area. In some energy ranges, making the shield thicker actually increases the number of secondaries that get into the habitat. You have added mass, paid for it with propellant and engine power, and turned part of your shield into a source of extra radiation. So now you are stuck balancing between too thin and too thick. Too thin and the primaries slice straight through people and electronics. Too thick in the wrong materials, and you boost the secondary showers. Designers look to hydrogen-rich materials like water and plastics to slow particles gently, but perfect solutions do not exist. You might line sleeping quarters with water tanks and food stores, turn life support resources into partial radiation shields, and still only cut the dose, not eliminate it. On Earth, you hardly think about any of this. The atmosphere above you, about 10 kilometers thick, 6 miles, plus the planet's magnetic field, shred and bend away most cosmic rays. By the time particles reach sea level, the flux is tiny and softened. In interstellar space, there is no thick air above you, no global magnetic shell. The sky around your ship is always active, always sending these particles through your hull and through your body. You do not feel them directly. There is no burn, no flash, just a very slow increase in damage. Over decades, that slow damage starts to look like early aging. DNA repair systems get hit again and again. Cells accumulate mutations, some die, some go cancerous. Blood vessels in the brain and heart see more wear. Nerve cells, especially in sensitive regions, can be injured in ways that show up later as cognitive decline, mood disorders, memory problems. The risk is not just maybe more cancer at 80, it is your crew in their 50s might function like people much older, right when you need them to manage the hardest parts of the mission, and that is only for the people. Your electronics and materials are also under constant fire. Single event upsets, where one particle flips a bit in computer memory, become routine. Over time, components fail permanently as atoms are knocked out of crystal lattices, insulators break down and solder joints weaken. Radiation-hardened designs can slow this, but for a mission measured in decades, the line between hard enough and still too fragile is thin. So inside the heliosphere, the sun tries to kill you with bursts, storms, spikes of radiation that show up on certain days. Beyond the heliosphere, the danger is the opposite. No big spikes, just a constant background level that is always too high. There is no safe season, no quiet solar minimum that gives you a break. You live in a steady radiation storm that never turns off. That means if you survive vacuum acceleration, engine hazards, microgravity, and early solar storms, you still face a long, slow lottery where every extra year in deep space adds more invisible hits to your body and your ship. Even before you get close to Alpha Centauri, crew members might already be developing cancers, subtle brain changes, or heart problems that trace back to billions of tiny collisions that happened hundreds of billions of kilometers earlier. And all of this is happening while space still looks empty to your eyes. But it is not empty. Even in the cleanest parts of interstellar space, there is dust and there is gas. At normal speeds, those are just traces. At 10 or 20% of light speed, each tiny grain of dust, each clump of atoms carries enough energy relative to your ship to behave less like a harmless speck and more like a high-powered weapon. You handled radiation and microgravity, but there is something else waiting in front of your ship, and it does not care how good your reactors or your life support are. It is the dust between the stars, and at a fraction of light speed, every tiny grain turns into a weapon aimed straight at you. Interstellar space is often called empty, but it is only empty compared to air. There is still dust out there, tiny solid particles, often smaller than cigarette smoke, spread through the gas. The typical mass of dust in a cubic meter of interstellar space is extremely low, somewhere between 10 to the minus 26 and 10 to the minus 23 kilograms per cubic meter, depending on the region. That is like taking a few grains of smoke or soot and spreading them out in a volume the size of a house. On a human scale, that sounds like nothing, but your trip to Alpha Centauri is not a few meters. It is around 4 times 10 to the 16 meters, about 4.37 light years. Your ship, maybe with a cross-section of a few hundred square meters, plows through a staggering volume of that almost nothing during the journey. When you multiply a tiny density by a huge volume, you end up with real mass. Over the whole path, your forward shields and bow will run into many, many grams of dust, maybe more, and every bit of that mass arrives with enormous relative speed. So how bad can a single dust grain really be? Take one speck with a mass of around 10 to the minus 12 kilograms, a few micrometers across, too small to see with your eyes. Now give your ship a speed of 20% of light, about 60,000 kilometers per second, roughly 37 million miles per hour. Using the standard kinetic energy formula, the grain carries on the order of a couple of thousand joules of energy in the ship's frame. That is in the same ballpark as the energy delivered by a rifle bullet. The difference is, a rifle bullet is millimeters across and already easy to miss or stop with armor. This dust grain is invisible to the naked eye, and it is not one impact in a controlled test. It is one of many impacts, scattered randomly across your forward surface. If even one grain like that hits a weak point, a thin section of hull, a coolant pipe, a cable bundle, a sensor head, it can punch through and cause damage completely out of proportion to its size. And that is just for an ordinary tiny speck. Larger grains, say the size of fine sand, carry far more energy, scaling with mass and the square of velocity. A 10 million times heavier grain at the same speed does not just poke a hole, it behaves more like a small explosive, dumping a massive burst of energy into a very small volume of your ship's material. The impact physics at these speeds do not look like everyday collisions. At orbital speeds of a few kilometers per second, which we see with space debris around Earth, impacts already behave more like explosions. Material on both sides, the projectile and the target, is compressed, heated, and vaporized. Shockwaves propagate through the metal, and fragments called spall blast away from the impact site. At tens of thousands of kilometers per second, a significant fraction of light speed, you push into a regime that is usually studied in nuclear weapon effects and very high energy physics. The material in the path of the grain is compressed so hard and so fast that atoms are ionized into plasma. A small volume of solid hull turns instantly into a hot, expanding cloud. That cloud and the shockwave around it can rip through layers of structure. Even if the main hull plate does not crack in a visible way, the back side of it can shed a spray of molten and solid fragments that shoot into the spaces behind it, cutting cables, puncturing tanks, and killing anyone unlucky enough to be in line. You cannot rely on simple, thick armor to save you, because the goal is not to stop a slow rock, it is to manage the energy release from an ultra-fast particle in a way that does not dump the worst of it into your crew compartment. That is where shield design changes. Real satellites today often use what is called a Whipple shield. Instead of one thick wall, they have a thin outer bumper, a gap, then the main pressure hull. A small piece of debris hits the bumper, shatters into a cloud, and that cloud spreads and slows a bit before it reaches the main wall, reducing the local damage. For interstellar speeds, a simple two-layer Whipple shield is not enough. You may need multiple spaced layers, each one breaking and spreading impacts more, with several meters of separation and sacrificial material between them. In front of all that, you might fly a thin, separate shield or debris sail some distance ahead of the main ship to take the very first hits and generate a protective plasma cloud. All of this shielding has mass, and not a little. To get serious protection, you may end up dedicating thousands of tons just to sacrificial armor on the bow. Every extra ton is something your engines must push up to 10 or 20% of light speed and later slow down again. The rocket equation punishes that mass brutally. But if you guess low on the dust density along your route, or you underbuild the shield to save fuel, you are betting that you will not meet any bigger grains than you planned for. The ugly part is, you do not get much warning when that bet fails. A grain the size of a sand particle, hitting the wrong spot in the forward shield or slipping through a weak area, can breach layers you thought were safe. That failure can be instant. One moment the ship is cruising normally, the next a forward tank ruptures, a radiator manifold is torn open, or a structural rib snaps. The crew might not even know what happened before life support starts to fail. So why not just scan ahead and dodge the threats, like a plane dodging a storm on radar? At the speeds we are talking about, your reaction time window is ridiculously small. At 0.2 c, you cross 60,000 kilometers every second, roughly half of Earth's diameter. To react to something 1 kilometer in front of you, you would have about 1/60th of a thousandth of a second. That is much shorter than the time it takes light to go from the object to your detectors and back, and much shorter than any reasonable control system can respond. You can try to look much farther ahead, tens of thousands of kilometers or more, but then you run into another problem. The dust grains are tiny and very hard to see at long range. Radar beams spread out and lose strength. Reflections from micrometer-sized particles are extremely weak. And the background noise from your own engine, plasma, and electronics is high. High-power lasers and LiDAR have similar issues, and at these speeds, by the time you have a clear reading, you're already too close. That leaves you with one practical strategy. You do not dodge most grains, you accept that you will hit them, and you build the front end of the ship to soak up those hits without letting them through to the fragile parts behind. Your success or failure comes down to your shield design, your choice of speed, and your estimate of the dust environment. If your math is right, the outer layers ablate and erode over years, but the inner hull stays intact, and you arrive at Alpha Centauri with a chewed-up nose but a live crew. If your math is wrong, the very first unshielded speck of matter you run into, something so small you could not even see it between your fingers, ends the mission instantly, long before cosmic rays or long-term health problems can do their work. And dust is only part of the material you slam into out there. Even where there are no solid grains, there are still atoms, mostly hydrogen, scattered through space. At everyday speeds, those atoms are harmless. At 10 or 20% of light speed, each single proton or atom becomes a microprojectile, and over trillions of kilometers, those microprojectiles add up to a new kind of threat, turning the very thin interstellar gas itself into a slow, grinding weapon against your ship. You can strip every visible grain of dust out of your path and you are still not safe, because at high enough speed, even the thinnest gas between the stars turns into a slow, constant attack on the front of your ship. The space near the Sun has a typical interstellar hydrogen density of around 0.1 to 1 atom in each cubic centimetre. That is about 100,000 to 1 million atoms in every cubic metre. On human cells, that is as close to nothing as you will ever see. But your trip to Alpha Centauri is about 4 times 10 to the 16 metres long, and your ship is not a point, it has a front area. Take a cross-section of just 100 square metres, about the footprint of a small house, and push that through the whole distance. Now multiply 100 square metres times 4 times 10 to the 16 metres, gives you 4 times 10 to the 18 cubic metres of space that your bow sweeps out. Multiply that by the number of hydrogen atoms per cubic metre, somewhere between 10 to the 5 and 10 to the 6, and you get roughly 10 to the 24 to 10 to the 25 atoms passing through your forward cross-section during the trip. That adds up to only a few grams of hydrogen in total, like a small coin in mass. On a scale where your ship weighs 1,000,000 kilograms, 1,000 tons, a few grams sounds like nothing. The problem is, those few grams do not arrive gently. In your frame, they slam into the bow at a large fraction of light speed. At 20% of light speed, about 0.2 c, each individual proton from that hydrogen carries a specific amount of kinetic energy. Using the basic rule that kinetic energy goes as 1/2 the mass times the speed squared, you can plug in the mass of a proton and a speed of about 60,000 kilometers per second, roughly 37 million miles per hour. The result is on the order of 3 times 10 to the minus 12 joules per proton. That is an absurdly small number per particle, but you're not dealing with one proton, you are dealing with around 10 to the 25 of them over the journey. Multiply that small energy per proton by the huge number of protons, and the total energy dumped into your forward structures is around 3 times 10 to the 13 joules. That is comparable to the explosive yield of several thousand tons of TNT spread out in time and space along the nose of your ship. It is not one big blast, It is a long, grinding energy transfer into whatever material you used for the bow and shield. Each individual impact is tiny, but every proton that hits the bow transfers momentum, generates a little heat, and in many cases ionizes atoms in the shield material. The outermost layer of your hull is constantly being slammed by these microbullets. Over time, you build up a thin region of super hot, partly ionized gas in front of the ship, a kind of plasma sheath that rides on the bow. That sheath does not just sit there. It radiates energy, including high-energy photons like X-rays, back into surrounding structures. It carries electrical currents and charges, which can couple into the hull and into external equipment. It slowly erodes the forward shield through processes similar to very fast sandblasting, just with each grain carrying much more energy than normal sand. Over years, millimeters or even centimeters of material can be knocked away or changed in structure, making the leading edge thinner, weaker, and more likely to fail when a larger dust grain or a structural load arrives. You can try to fight this by not letting the protons hit solid matter at all. Since they are charged particles, you can, in principle, bend their paths using electric or magnetic fields. That leads to the idea of magnetic or electrostatic deflectors in front of the ship. Vast structures that generate a field strong enough to curve incoming particles around the hull before they ever touch metal. In practice, that means superconducting coils producing magnetic fields of many Teslas over distances of tens of meters, or huge charge grids at high voltage. For reference, the magnets in powerful MRI machines in hospitals reach a few Teslas. You would need fields that strong or stronger, scaled up around an entire spacecraft. The mechanical stresses in those coils would be enormous, because strong magnetic fields push and pull on the conductors that make them. The supporting structure has to hold that tension day after day, year after year, under radiation, thermal cycling, and vibrational loads from the engines. Superconductors are also fragile in one important way. If part of the material warms above its critical temperature, it quenches, losing its superconducting state. The current then dumps heat into the coil, the field collapses, and your carefully shaped shield vanishes. If that happens while you are cruising at 0.2 C, then in a matter of seconds you go from deflecting most of the incoming protons to taking them straight on. The interstellar gas, which was a background nuisance before, suddenly becomes a direct source of heating and erosion. If your solid shield is already thin from years of slow wear, that switch can push you fast towards structural failure. At even higher cruise speeds, 30%, 50% of light speed, the situation gets more extreme. The kinetic energy of each incoming particle rises sharply as speed increases. At those energies, when a proton or a helium nucleus hits the atoms in your shield, the collision is violent enough to trigger nuclear reactions in the material. Nuclei can shatter in a process called spallation, shedding neutrons and lighter fragments. Under some conditions, you can even get limited fusion reactions, where light nuclei like hydrogen combine in the impact zone. Now your forward shield is not just hot and eroding, it is becoming radioactive. It starts to generate its own field of secondary neutrons and gamma rays that then stream back into the rest of the ship. The very structure that is supposed to protect you from the outside environment turns into a new radiation source parked a few tens of meters from your crew modules. Any maintenance task near the bow gets harder and more dangerous, and if the shield is large and heavily activated, that radiation adds to your long-term dose, on top of cosmic rays and everything else. So interstellar gas, which sounds harmless when you say a few atoms per cubic centimeter, becomes another hard constraint on how fast you can safely travel and what kind of front-end design you can use. Push the speed too high and the constant, unavoidable interaction with hydrogen and helium between the stars eats your shield, heats your nose and bathes your ship in extra radiation. The deeper problem is that almost every fix you consider, thicker solid shields, bigger magnetic fields, higher voltages, comes with a cost in mass, complexity, and new failure modes. Add a huge coil to bend protons away, and now that coil itself can crack, quench, or overload. Add more solid material to soak up particles, and now that material can turn into a radioactive source and a generator of secondary showers. Sooner or later, you run into a harsh design paradox. The more protection you bolt onto your ship to fight dust, gas, and radiation, the more you increase the mass you need to push, the energy you must handle, and the number of new ways your own shielding can turn around and injure you. The line between safety system and the thing that kills you first gets very thin. More armor sounds like the obvious fix. Throw metal at every problem and call it safe. But at interstellar speeds, every extra slab of protection you bolt on can quietly push you closer to failure, sometimes faster than the thing you were trying to block. Start with the basic trade mass versus speed. Every single kilogram of shielding you add at the design stage has to be pushed up to 10% of light speed, maybe 30,000 kilometers per second, about 19 million miles per hour, and then slowed back down at the other end. Rockets do not pay for speed in a straight line, the math is exponential. When you increase the dry mass of the ship, the part that is not fuel, you do not just add a little bit more propellant, you very quickly need a lot more, often multiplying the fuel load to gain the same change in speed. So you stack on thick armor plates, the total mass goes up, then you need bigger propellant tanks, which are more mass, which means even bigger engines, which are more mass again, all of which need more structure to hold them together under thrust, which is more mass. Soon your attempt to protect the crew with thicker walls has forced you into a ship that is heavier, longer, and more mechanically stressed. Under long burns at even 1G, that extra weight can push the engine mounts, trusses, and propellant tanks right to the edge. Overshield far enough and the first thing that fails at speed is not the radiation barrier, it is the engine system or the frame itself tearing under its own load. That is already bad, but there is a second catch. Thicker shields do not always mean less radiation dose for the people inside, especially when the radiation comes from very high energy particles. Think about a single heavy ion from a cosmic ray, maybe an iron nucleus with an energy of several billion electron volts, hitting a piece of aluminum 1 centimeter thick. It does not just slow down and stop neatly. It slams into the atoms in that metal and shatters, producing a whole cascade of fragments, lighter nuclei, neutrons, and other secondary particles that go spraying in all directions. Instead of one particle going in a straight line, you now have dozens of projectiles, some bouncing around inside the material, some making it through to the space behind. From the crew's point of view, that looks like a spray of invisible shrapnel spreading through their cabin. In some energy ranges, if you make the aluminum thicker, you actually increase the number of secondaries that leak into the habitat volume. A thinner wall lets more primaries through, but fewer of them fragment inside the material directly around the crew. There is a sweet spot, and going heavier than that does not help. It hurts. So material choice becomes just as important as thickness. Not all shields behave the same way under nuclear scale hits. Hydrogen-rich materials like water and many plastics tend to be better at slowing down protons and stopping neutrons without creating as many nasty secondaries. Very heavy elements, like lead, are great for stopping X-rays and gamma rays, but when a cosmic ray heavy ion hits lead, it tends to make big cascades of fragments. That means you might literally be safer sleeping next to tanks of water, bags of food, and walls lined with plastic than you would be behind slabs of lead. The downside is obvious. Those soft materials are not just shields, they are also your life support. The water is what you drink and use to grow food, the hydrogen in plastic might be part of your structural composites, the food is your basic survival. You often end up wrapping crew quarters in rings of water tanks and storage to get that double use. Now picture an accident, a fire in a storage bay, a micrometeoroid hit that rips a hole in a tank, or a leak that forces you to dump contaminated water. You do not just lose supplies, you strip away the radiation armor around the cabins. Overnight, your dose rate can jump, and the long, quiet cancer and organ damage risks rise sharply. Even with the right materials, you probably cannot afford to shield the whole ship equally. The engines and reactors at the back can tolerate much higher radiation levels than human bodies can. Many nuclear spacecraft concepts use a shadow shield, a thick, dense block positioned between the reactor and the habitat. That shield only protects a narrow cone of space downrange. In that shadow, the crew lives in acceptable radiation levels. Everywhere else around the reactor, the radiation is intense. That design saves a lot of mass, but it creates a sharp geometric hazard. As long as the ship's attitude control keeps the habitat locked into that safe cone, you are fine. If a guidance system glitch, a control jet failure, or a collision causes the ship to yaw or pitch so that the crew module swings out of that shadow, suddenly there is no shield between them and the active reactor. In minutes, they could take a dose that would normally be spread over years. Orientation becomes a life support parameter. A bad automatic maneuver at the wrong time can turn normal operations into an accidental reactor exposure. Then there is the temptation that hits every cautious engineer, designed for the absolute worst case. What if the ship meets a dust grain the size of a small rock, not just micrometer dust at a once-in-a-million-years object on that exact path? To survive that, you start drawing bow shields that are meters thick, made of exotic composites backed up by additional layers and magnetic fields. On paper, you can always write a bigger number and say, now it survives that grain too. But each new just-in-case layer adds mass, complexity, and new failure points. At some point, the ship is so massive that it cannot practically reach the needed cruise speed with any engine you can reasonably build. You either accept a much lower speed, which stretches the travel time from decades to centuries, or you accept a much higher fuel fraction, which might make the structure so fragile and overloaded that it fails under thrust. Drop the speed, and a different set of killers becomes certain instead of just possible. Cosmic ray dose from the background goes up simply because you're out there longer. Mechanical fatigue from endless cycles of heating, cooling, spinning and thrusting accumulates. Psychological stress and generational issues grow because now you're talking about journeys that outlast human lifespans. In trying to protect yourself against an ultra-rare high-energy dust hit, you might force the mission into a profile where slow, guaranteed processes like cancer, aging, and material decay get enough time to win. So shielding in deep space is not a simple game of more is better. It is a narrow, constantly shifting compromise. Too little and you die quickly from radiation, dust, or gas impacts. Too much, or in the wrong materials and places, and you create particle showers, reactor exposure risks, and a ship so heavy and stressed that it may never complete the trip. And all of this, all the mass and complexity and risk, is just to keep the worst of the outside environment away from a fragile pocket of air and water inside. Because even if your shielding is perfect, one small leak in that pocket, one failure in the systems that manage oxygen, carbon dioxide and water recycling can kill you faster than any distant star or dust grain. All the exotic threats out there don't matter if you lose the basics inside. If the air and water inside the hull slip even a little out of balance, your trip to Alpha Centauri ends long before any dust grain or cosmic ray reaches you. Start with air, because your body is a chemical machine running on oxygen. An average person burns through around 0.8 kilograms of oxygen per day and turns it into roughly 1 kilogram of carbon dioxide. With 10 people on board for 40 years, that is tens of thousands of days of breathing. If you tried to carry all the oxygen as a one-time supply and never recycle it, you would be talking about roughly 120,000 kilograms of oxygen, around 120 metric tons, just for breathing. That is the mass of a small ship all by itself, so you have no choice, you recycle. Modern systems, like the ones on the International Space Station, strip carbon dioxide out of the air using chemical sorbents, and then use machines like electrolyzers to split water into oxygen and hydrogen, feeding the oxygen back into the cabin. This kind of regenerative life support is efficient, but it is also complex and touchy. It depends on pumps, fans, valves, membranes and software, all operating in the right range. If the carbon dioxide scrubbers underperform for even a few days, levels start to climb. On Earth, normal outdoor air has about 400 parts per million CO2. Indoors, a few thousand parts per million just makes the room feel stuffy. On your ship, if it rises toward 1 to 2%, about 10,000 to 20,000 parts per million, you start to get headaches, fatigue, and trouble concentrating. push it higher, and you hit confusion, panic, and then loss of consciousness. This can happen while oxygen levels still look okay on one display. You can suffocate in a room that technically has enough oxygen simply because the carbon dioxide went too high and poisoned your breathing. Air is only half the story, the other half is water, because that is the fluid running through almost every system that keeps you alive. Each person needs on the order of 3 to 5 litres of drinking water per day, plus water for food, washing, and cleaning. In a closed life support loop, you do not send that water one way, you reclaim it. Urine, sweat, and exhaled moisture are captured, filtered, distilled, and turned back into clean water. With good hardware, you can recycle more than 90% of what you use, but that last 10% over years still adds up, so you start with big reserves, thousands of litres, thousands of kilograms. On an interstellar ship, that water also does double and triple duty. Tanks of water wrapped around the crew quarters act as radiation shielding, because hydrogen atoms are good at slowing down protons and neutrons. Water acts as the thermal buffer, soaking up heat spikes from equipment and helping stabilize temperatures. Lose a purification unit to a mechanical fault, or have a tank breached by an impact or internal failure, and you take multiple hits at once. You lose drinking water, yes, but you also strip away part of your radiation armor and part of your thermal stability. Suddenly, the same cosmic rays and solar particles that were marginal become more dangerous, and temperature control has less margin. You went from annoying leak to whole ship vulnerability in one break. Even if you have enough air and enough water on paper, you still have to keep them inside the ship, and that means every seal, weld, and valve matters. A leak in space does not have to be dramatic to be deadly. A hole only a few millimeters across, something you could barely see if it were in a pipe at home, can vent litres of air every minute depending on the pressure difference. At standard cabin pressure, around 101 kilopascals, about 14.7 pounds per square inch, that flow adds up. Over a few hours, that small leak can drop the cabin pressure far enough that the partial pressure of oxygen falls below what your lungs need to move oxygen into your blood. You start feeling short of breath, dizzy, then you black out. On the ISS, a possible leak triggers an immediate hunt. Astronauts close hatches, listen for hissing, use ultrasonic detectors, track pressure over time. They have ground control helping with data and planning, and they are only a few hundred kilometers above Earth. On a big interstellar ship with lots of compartments, long tunnels, and complex structures, finding a slow leak can take far longer. Sensors might only show a very gradual pressure drop over weeks. If you underestimate it or push repairs down the to-do list, you might suddenly find that the margin is gone. Then the first real killer in your trip is not a star or an engine, it is a small crack in plumbing or structure that nobody noticed in time. Air inside the ship has another threat, not just running out, but becoming dirty in ways your lungs and brain cannot handle. Every plastic, paint, glue, and piece of equipment releases small amounts of chemicals into the air, a process called off-gassing. Cleaning solvents, coolants, any mishandled chemical add to that load. On Earth, fresh air and ventilation dilute and carry these away. On the ship, there is no outside. Your filters and scrubbers are the only way out for these vapors. If some compounds slip through because filters age or get saturated, you can see slow buildup of toxins causing headaches, nausea, irritation, or long-term organ stress. Then there is a small electrical fire in a panel does not just burn some plastic, it pumps smoke particles and gases like carbon monoxide and hydrogen cyanide into a sealed volume. Even low concentrations of these can be lethal in minutes. You can't just open a window to clear the air. You have to put the fire out fast, then scrub every cubic meter of the atmosphere clean with filters and chemical absorbers. Those systems have to work just as reliably as your oxygen and carbon dioxide controls, not for months, but for decades. A fire that would be a minor incident in a building on Earth can turn into a ship-killing event simply because the contamination has nowhere to go. Underneath all of this is one final dependency that you cannot escape. Everything that keeps your air and water in the safe zone runs on electrical power. Fans that move air, pumps that circulate water, heaters that prevent lines from freezing, chillers that pull heat out, carbon dioxide scrubbers, electrolyzers that split water, control computers that make decisions. Every one of these needs a stable power supply. If a major power bus fails, if your main reactor shuts down and your engines go quiet, you flip from exploration mission to survival countdown immediately. Batteries and backup fuel cells can keep key systems alive for a while, but not forever. As power runs low, you have to choose what to shut off. Maybe you cut lighting, then non-essential electronics. Then you start cutting into essential systems, maybe reducing air circulation, slowing water pumps, lowering temperatures. Pockets of stagnant air can form with CO2 pulling in corners, making local dead zones where someone can pass out silently. If you cannot restart the main reactor or bring up alternative generation before the backup runs dry, your air will drift out of spec, your water will stop cycling, temperatures will slip, and the ship will slowly but certainly become unlivable. On the ISS, people on the ground watch every parameter, send up replacement parts and plan around failures. If something truly catastrophic happened, the crew could get into a capsule and be on Earth in a matter of hours. At a few light years distance, there is no resupply and no rapid advice. Even if you could send messages at half the speed of light, a round trip takes around 8 years. By the time a detailed troubleshooting plan comes back, either you solved it yourself or everyone on board is already dead. So while the outside of the ship is fighting dust, gas, radiation and high-speed impacts, the inside is balanced on a narrow technical edge. A few pumps, a few tanks, a few software systems all have to keep a bubble of air and water in the right range, day after day, year after year. If they drift, you suffocate, poison yourself, overheat or freeze long before you see another sky. And even if every life support system works as designed, there is still one more layer of slow failure to deal with. The ship itself, the metal, composites, seals and joints that hold all this machinery together are aging, cracking and wearing out under you, turning the structure into yet another potential thing that kills you first. You can keep the air clean, manage radiation, and protect against dust and still lose. Because the thing you are standing inside is not eternal. The ship itself is slowly breaking underneath you, and you may not notice until it is too late. Every time you fire the engines, the structure flexes. Every time you spin up a habitat ring for artificial gravity, then spin it down again. The joints, beams and panels feel changing loads. Metals and composites are not perfectly rigid. They bend a tiny bit, then spring back. Do that once, nothing happens. Do it millions or billions of times over 40 years, and you start to get micro cracks, tiny fractures at stress points, welds, bolt holes and joints. On aircraft, this shows up after tens of thousands of flight hours, and we already retire planes or inspect them very carefully because of it. A starship is like a plane that never lands, never gets fully unloaded, and never goes into a hangar for a full rebuild. A crack that grows only a few micrometers per year can seem harmless, but in a few decades it can turn into a centimeter scale defect in a critical girder or pressure frame. One day that piece is just a bit stressed. The next day a normal thrust cycle pushes it past its limit and it snaps, and now you have a cascading structural failure moving through the frame faster than anyone can respond. While mechanical stress is working from the macroscopic side, radiation is chewing at the materials from the inside. High-energy particles, the same cosmic rays and solar ions that hurt people, also displace atoms in solids when they strike. In semiconductors, a single hit can flip a bit, causing a one-time glitch, but over time many hits cause permanent damage, breaking crystal lattices and making transistors fail. Insulating materials like the plastics around wires and the dielectrics and capacitors slowly embrittle under radiation. They crack, lose flexibility, and their electrical properties shift. Plastics that started out tough and flexible, used in seals, hoses and gaskets, get harder and more brittle. They discolor, and they stop sealing perfectly. After enough years, cables can develop cracks in their insulation, exposing conductors, which raises the risk of shorts and fires. Circuit boards can develop conductive paths where there should be none, or open connections where there should be contact. A single stuck relay or failed control board at the wrong time can shut down a pump, lock a valve, or take an entire subsystem offline. In the environment of a starship, that can be the first domino in a chain that ends with life support or propulsion loss. Vacuum itself adds more slow damage. Many materials, especially polymers, contain small amounts of trapped gases left over from manufacturing. In a hard vacuum, these gases slowly leak out, a process called outgassing. As they escape, they can change the mechanical properties of the material, making it weaker or more brittle. The released molecules can drift and condense on cold surfaces, like optical sensors, camera lenses, star trackers, and radiators. Over time, those delicate surfaces get coated with thin films that block light, change reflectivity, and reduce efficiency. A star tracker with a slightly fogged lens might start giving incorrect orientation data, leading to guidance errors. Metals in contact under vacuum have their own issue, called cold welding. Without a layer of oxide or contamination between them, very smooth metal surfaces pressed together can fuse as if they had been welded, even without heat. Parts that were designed to slide, rotate, or separate can instead lock solid. A valve in a coolant line that is rarely moved might, the one time you need it, refuse to turn, a hinge on a radiator panel might not deploy when commanded. A stuck mechanism like that can block heat rejection, stop fluid flow, or prevent antennas and shields from moving into their safe positions. The forward parts of the ship, the leading edges and primary shields, are in even worse shape because they're not just sitting in vacuum, they're getting hit constantly by high-speed particles. At 0.1 C, 10% of light speed, dust grains and hydrogen atoms pile up into a thin, hot plasma all around the bow. That plasma can knock atoms out of the surface in a process called sputtering. Each impact takes a few atoms away, but over years and decades those impacts remove measurable thickness. So you start with a shield plate that is, say, a few centimeters thick, and very slowly it is shaved down. Sensors buried behind it might start to show higher radiation levels. Thermal readings might show hotter spots where the shield is thinned. If monitoring's perfect and the crew is on top of inspections, you can spot this and plan repairs or reinforcements. If instruments drift, logs get ignored, or a decade of no problems makes people complacent, the first real sign of failure might be when a slightly larger particle slams into a spot that is now dangerously thin and punches straight through into tanks or compartments that were never meant to take a direct hit. All of this means that maintenance is not a side job on a starship, it is a full-time fight against the natural decay of materials. On Earth, when something ages out, you retire it. Planes are taken out of service, oil rigs are decommissioned, satellites, once they break, are written off and replaced. In orbit, we bring crews down after months, refurbish hardware, then fly again. On an interstellar mission, you do not retire the ship, you live inside your one and only prototype for decades. The crew has to be more than just pilots and scientists. They have to be machinists, welders, electricians, software techs, and inspectors. They have to cut and shape replacement parts from raw stock, improvise repairs when the exact spare does not exist, and decide which cracks are safe to watch and which demand immediate action. They are doing this while tired, aging, and under the same radiation and psychological stresses as everyone else. Spare parts are finite. You can bring a big stock of fasteners, circuit boards, pipe, and plating, but every repair eats into that stash. After 20 years, the ship no longer looks like the thing that left Earth. It looks like a patched, modified, improvised structure held together by human judgment and old documentation. If the crew misreads a structural issue, calls a major crack cosmetic, or decides to risk one more full-power burn on a truss that is actually near failure, the entire skeleton of the ship can let go. When that happens, there is no soft failure mode. A primary beam breaking under thrust can shear tanks, snap cables, and twist habitats. A rotating ring with a growing crack can suddenly tear apart, sending fragments spinning off like shrapnel into other modules. Floors can literally buckle under you. The end does not look like a slow fade. It looks like a sudden breakup, debris and air venting into space with no rescue path. So even if you keep the outside environment under control, your ability to survive rests on an aging machine that is always trying to fall apart. The longer you are out there, the more chances there are for a hidden crack, a brittle cable, or a fused valve to pick exactly the wrong moment to fail. And all this slow mechanical death is happening around people who are also under slow pressure, because it is not just metal and plastic that struggle with decades in a closed tube headed into darkness. Human minds do too, and if the structure does not snap first, the crew's own psychology might. You can armour the hull and harden the electronics, but you still carry the one system you can't redesign from scratch, your own brain. And it was never built for 40 years in a metal tube with no way out. First problem is simple and brutal monotony. Day after day you see the same walls, the same corridors, the same few faces, the same instruments. Outside the window, the starfield barely changes. There is no weather, no streets, no crowds, no forests, just machinery and routine. On Earth, people in Antarctic bases or submarines already show higher rates of depression, anxiety and conflict after just a few months. Now stretch that from months to decades. Boredom stops being a minor annoyance and starts acting like slow sandpaper on your mind, wearing down patience, motivation, and the ability to care about the checklist in front of you. Next is yesolation, and here physics itself joins the attack. Once you are a few light years away, the speed of light turns communication into a one-way wall. A message you send to Earth takes years to arrive, and any reply takes years to come back. Real-time talk disappears. No live video, no calls where someone on Earth says, "How are you?" and here's the answer. Even social media, the fast back and forth people are used to, is gone. You can send long messages and get long replies, but they are always delayed, always out of sync with how you feel now. After a while, home stops feeling like a real place with real people and starts to feel like an old recording you sometimes play back. Humans are wired to live inside a web of constant feedback from other brains. Cut that feedback to almost zero, and people can slide into a sense that nothing outside the ship is actually real anymore. That mental drift hits sleep and daily rhythm too. Your body runs on about a 24-hour internal clock linked to light and dark. On the ship, there is no sunrise or sunset unless you fake them with lamps. If schedules are consistent and the lighting is controlled, you can hold a stable day-night cycle for a while. But emergencies, maintenance demands, and shift work start to pull people into odd hours. A coolant line fails at night. A dust alarm goes off right before you are going to sleep. A system upgrade needs to happen during someone's usual rest period. Over time, you get chronic sleep debt, where most of the crew is always a little bit tired, reaction times are always a little bit slower, and judgment is always a little bit worse. On Earth, chronic shift work is already linked to higher rates of heart disease, mood disorders, and cognitive decline. On a starship, the cost is higher. A tired person can misread a gauge, forget to reopen a valve after a test, or skip a final verification step. In this environment, one missed step is not just an oops, it might be the start of a chain that vents air, overheats a system, or mispoints a radiator. Then there is the social pressure cooker. A crew of maybe 10, 20, or 50 people is locked in the same structure for years, maybe their entire adult lives. Conflicts do not have space to cool off. You cannot walk away to another city, another job, another circle of friends. Old arguments can resurface over and over. Small personality clashes can grow into deep grudges. We already see hints of this in Mars habitat simulations and Antarctic stations, where even trained, screened, motivated groups get friction, cliques, and emotional breakdowns over relatively short missions. On a multi-decade ship, those effects have time to build. Factions can form. Some people side with strict discipline and safety. Others want more comfort and risk-taking. Leaders can lose trust. In extreme cases, interpersonal violence, sabotage, or refusal to follow orders become realistic outcomes, not just movie scripts. If even one crew member decides that the mission is a mistake or that a leader is a threat, they can act in ways that put hardware and lives at risk. And here is the part that kills missions without any dramatic explosion: apathy. You do not need active sabotage to die in deep space. You just need people who slowly stop caring. If the mission starts to feel pointless, if the goal at Alpha Centauri is decades away, and everyone they loved on Earth is already dead or unreachable, the mental reward for doing careful, boring maintenance drops. That subtle shift is dangerous. Instead of a full inspection, someone glances at a panel and says, "Looks fine." Instead of logging a strange noise from a pump, they assume it is nothing. A warning light that flickers gets mentally filed as that glitch again and ignored. A slow CO2 creep, a tiny pressure drop, a vibration in a truss. Any of these can sit in the background for weeks because fixing it would mean more effort today for a payoff that feels abstract and far away. By the time anyone decides to take it seriously, the small issue can have grown into a major fault. So even if you have perfect designs and enough spare parts, the weak link is still the human attention span and human motivation stretched across decades. The mind that once memorized emergency procedures and could run simulations in its sleep might, 20 years in, decide that skipping one drill is fine, skipping one test is fine, skipping one inspection is fine. That is how a ship that is technically repairable dies, not because it could not be saved, but because the people inside it were too tired, too numb, or too detached to save it in time. Now, connect this to one more layer of complexity. On a trip this long, it is not enough to just store food and replace filters. You probably need a living ecosystem on board. Plants, microbes, maybe animals, all in a closed loop. That ecosystem is even more complex and even easier to break than metal and pumps. If your crew is already struggling to keep themselves mentally steady, how stable can a mini-biosphere stay under their care for decades? You're not just keeping people alive in a box, you are trying to run a whole mini-ecosystem in a box, and that system has more ways to fail than any reactor or engine you carry. Start with the biology you cannot see at all, the microbes in and on your own body. Your gut microbiome, the community of bacteria and other organisms in your intestines, helps you digest food, trains your immune system, and even affects mood and behavior through chemical signals. On Earth, that microbiome is constantly being refreshed by contact with other people, animals, soil, plants, and varied food. On a starship, your food is more limited, your environment is cleaned aggressively, and antibiotics may be used more often to control infections. Over years, that pressure can shift the balance of species in your gut. Some helpful strains may slowly fade out. Others, more resistant to antibiotics or better adapted to low-fiber processed diets, may take over. The result is not always dramatic at first, maybe more stomach problems, more food sensitivities, more subtle immune issues. But with no easy way to reintroduce lost microbes from the outside world, small imbalances can lock in. In a closed ship, a change that would just be a personal health quirk on Earth can spread across the entire crew because everyone shares the same limited biological inputs. Now scale up from the microbes in your body to the plants that have to feed you. You cannot realistically pack 40 years of food for 10 or more people in dry form without insane mass. At some point you need real agriculture on board, hydroponic or aeroponic farms, racks of plants grown in nutrient solutions instead of soil. To cover most of a small crew's calories, you are probably looking at hundreds to thousands of square meters of growing area, roughly the area of a supermarket to a small warehouse. Those plants need steady light, steady temperature, precise nutrient mixtures, and some method of pollination, maybe hand pollination, maybe small insects, maybe artificial systems. If any of those support systems glitch, yields drop. Worse, if a plant pathogen gets into the system, a fungus, a virus, or a bacterial disease, it has a perfect setup to spread fast. On Earth, a blight in one field can be isolated, burned, and replaced with seed from somewhere else. On the ship, your crops may all share the same genetics, the same water, the same air. A disease that hits your main staple like wheat, soy, or potatoes can rip through the entire farm. You might have emergency stores, freeze-dried rations, or concentrated food, but those are finite. They buy time, not safety. If you cannot recover the farm, the failure mode is simple. You run out of calories. Feeding plants is not just a matter of adding fertilizer out of a bag, because you cannot constantly import new fertilizer from Earth. Carbon, nitrogen, phosphorus, and other elements have to cycle through the system. Food goes into people, comes out as waste, and that waste has to be broken down by microbes in bioreactors or compost systems, then turned back into forms plants can use, like nitrates and phosphates in solution. Those systems are complex, full of pumps, mixers, and carefully balanced microbial communities. If a bioreactor culture crashes, if the microbial mix shifts, nutrient conversion can stall. Nitrogen might escape as gas and be vented during maintenance, slowly leaking out of your closed loop. Plants might appear to grow fine for a while, but yields drift down as the nutrient balance changes. You look at the farm and see green leaves, but the harvest weight month after month shrinks. That is how you can drift into famine even while everything looks okay. The system numbers, the mass balances have to be tracked obsessively, or you can slide past the point of easy recovery without noticing. Pathogens do not just threaten plants, they threaten the people running the system. In a closed population, sickness behaves differently than it does on a planet with billions of hosts. A virus that causes a short flu on Earth might circulate again and again in the small crew, flaring up whenever someone's immunity dips. Norovirus, stomach bugs, respiratory infections, any of these can knock out a big fraction of the crew at once if living quarters are tight. On Earth, you can call in extra staff, divert patients to hospitals and tap into huge pharmaceutical supply chains. On the ship, you have the medicines you brought, what you can manufacture on board, and that is it. If a pathogen evolves resistance to your limited set of antibiotics or antivirals, or if you simply run out, a simple infection can become a serious crew-wide crisis, especially if it hits during a period when heavy maintenance or navigation work is needed. That brings up one more quiet, long-term threat: mutation. The same radiation environment that chips away at your DNA also hits bacteria, fungi, and plants. Radiation increases mutation rates. In a big open ecosystem on Earth, most mutations wash out into the huge background. On a ship with a small closed set of genomes, mutations have a much easier time taking over. Over decades, microbes in your gut, in your waste processors, and on the farm can drift into new forms. Some might become more efficient helpers, but others can turn into more aggressive pathogens or degrade crucial processes. A microbe that used to break down waste into safe fertilizer could mutate into a strain that produces toxic byproducts instead. A mild plant fungus could, after many generations under radiation, become more virulent and kill crops faster. Plants themselves can mutate, losing yield, changing nutrient content, or becoming more sensitive to stress. You are basically running an evolutionary experiment in a sealed metal can, with radiation turned up and diversity turned down. There is no easy reset button. If your main nitrogen cycling bacteria pick up a harmful mutation and spread through all your reactors, you cannot call a supplier and order a fresh batch. You have to have archive backups or a way to rebuild from scratch. If your best crop line loses productivity due to accumulated mutations, switching strains in time requires that you kept enough genetic diversity in cold storage and that you notice the trend early. If evolution breaks your ecosystem badly enough, the failure does not look like a sharp disaster. It looks like a long slide. Each harvest is a bit worse. Each round of illnesses is a bit more severe. Each batch of processed waste returns a bit less usable nutrient. You switch to rations, then to tighter rations, then to just enough for now. Eventually the math stops working. The system cannot feed all the people and all the necessary microbes and plants. At that point, unless you massively change crew numbers or find some miracle supply, the end state is simple: you starve, not because you ran into an asteroid, but because biology in a box, under constant stress, finally cracked. And even if you somehow keep that artificial ecosystem balanced, keep the farms productive, microbes in line, and disease under control, you still face the one enemy you can never really turn off: time itself slowly stacking radiation damage, cancers, aging bodies, and aging minds on top of aging hardware. until one of those slow processes becomes the one that actually kills you first. Even if every alarm stays quiet and every big system works, time does not stop just because you left Earth. The longer you spend crossing that gulf, the more the slow background killers stack up. Radiation is the first of those slow killers. For a Mars trip, people already worry that a crew might pick up an extra 3 to 5% lifetime risk of fatal cancer from one mission. Stretch the exposure from a couple of years to several decades, even with good shielding, and the total dose can easily climb into the range of several civets over a career. Your body does have DNA repair systems, but they are not perfect. They just keep the damage manageable at normal background levels. Under a constant drizzle of high-energy particles, those systems get hit over and over. A few mutations get fixed, a few slip through, then a few more. On Earth, some of those slow mistakes turn into cancers that might show up in your 70s or 80s. On the ship, with higher radiation and no escape from it, those same processes can hit much earlier. You can have people who started the mission in good health, in their 30s, dealing with serious cancers in their 40s or early 50s, while they're still supposed to be key operators. Diagnosing and treating those cancers properly needs imaging, lab work, and specialist care that a small ship medical bay can barely approximate. You might be able to remove small tumours and give basic drugs, but advanced oncology is far beyond what a crew of a few dozen can provide for itself. Radiation and microgravity together also work on your nervous system and blood vessels in more subtle ways. There is growing evidence that long-term radiation exposure can damage brain tissue and blood vessels, and that microgravity changes how fluids move through your head. Over years, that combination may increase the risk of neurodegenerative diseases, things like dementia-like syndromes and Parkinsonian symptoms, decades earlier than normal. At the same time, your arteries and heart are under altered mechanical stress, which can feed into earlier strokes, heart attacks, and chronic circulation problems. So you start with a crew in their early 30s, peak physical and mental condition. After 40 years in this environment, even if individual people survive, the group you have is not a team of 70-year-old retirees with access to hospitals and family support. They are people who might have the biological wear and tear of someone in their 70s or 80s, while still being the only line of defense against a major system failure. Slower reaction times, weaker grip, cloudier memory, all at exactly the stage of the mission when high-stakes operations like deceleration and arrival need the most clarity and coordination. Meanwhile, while your bodies are aging, the ship is aging too, and the gap between what the hardware needs and what the crew can deliver keeps getting wider. Joints wear out, both human and mechanical. People develop arthritis in fingers and knees that makes fine repair work harder. Eyes slowly develop cataracts and other issues that blur vision. Hearing fades, making it easier to miss alarms or spoken warnings in noisy compartments. On Earth, you answer that by sending someone to a specialist, doing joint replacement surgery, fitting implants, or assigning lighter duty. On a starship, your medical bay is limited by what it can sterilize, what tools it can 3D print or machine, and what drugs and implants you stocked decades ago. Complex surgeries or advanced imaging might simply be impossible. That means some problems that are correctable on Earth, like a failing hip or a degenerating eye lens, can turn into permanent disabilities here. As more crew members collect more of these limitations, your collective capacity to respond fast and effectively to emergencies keeps dropping. If the mission length stretches beyond a single human lifetime, another layer appears. People are born and grow up on the ship. Those second-generation crew members never chose to leave Earth. They never had a life outside narrow corridors and artificial light. Their sense of home and normal is not a blue planet, it is this metal hull. The goal, Alpha Centauri, might be an abstract point in their future, not something they feel emotionally tied to. Their motivation and risk tolerance can be very different from the original volunteers. Some may be fully committed to the mission, others may resent it or simply not care whether the ship arrives in perfect shape or limps into the system half broken. The routines and safety culture drilled into the first crew can erode or mutate as stories are passed down. Maybe the second generation decides that some safety margins are paranoid and cuts corners. Maybe they prioritize comfort or personal freedom over strict maintenance schedules. You can design machinery and shielding to stay within specs. You cannot lock human values and culture into place with the same precision. Over decades, social drift can undo careful planning. Underneath all of this is the one rule you cannot rewrite: entropy. Closed systems tend toward more disorder. Lubricants slowly break down and gum up. Bolts that were torqued correctly work themselves looser, micrometer by micrometer. Dust, both from outside impacts and from internal wear, settles into electronics and moving parts. Software accumulates patches and workarounds, each one making behavior a bit more complex, a bit harder to fully predict. Memory in computers suffers bit flips from radiation, and some of those flips change settings or logs in ways that are hard to trace. Vigilant maintenance can push back against that trend, tightening bolts, replacing grease, cleaning contacts, refreshing software, checking checksums. But that vigilance depends on a crew that is healthy, motivated, well-slept and well-trained. As the years stack up, as people get tired, as priorities shift, more little things slip through. A sensor that failed years ago stays flagged as needs replacement, but never gets it. A backup pump that was disconnected for testing stays disconnected. Someone writes a temporary override that never gets removed. None of those small things kills you alone, but they combine: one missing backup here, one slightly cracked pipe there, one unpatched software bug somewhere else. Under the right conditions, they all line up. A flare hits, a dust grain punches a radiator, a tired crew member misreads a display, and a fault that would have been recoverable in year 5 becomes mission-ending in year 40, simply because too many small defences have been quietly eaten away by time. So even if you avoid fast death by vacuum, acceleration, radiation bursts, dust impacts, psychological breakdown, and ecosystem collapse, you are still walking a narrowing path between slowly rising biological risk and slowly decaying hardware. Time guarantees that something somewhere will eventually go wrong in a way you did not fully predict. And even if you somehow ride that moving target safely for decades, if the crew is still alive and the ship is still mostly intact when you finally reach Alpha Centauri's neighbourhood, you're not done. Because now you have to do the most violent thing of the entire trip. You have to get rid of almost all that speed without tearing the ship or yourselves apart. You finally reach Alpha Centauri's neighbourhood, the instruments show new stars ahead, and that's exactly when the mission becomes lethal in a new way. Because now you're not just a ship, you're a gigantic, uncontrolled bullet that has to somehow stop without tearing itself, or you, apart. At 10% of light speed, around 30,000 kilometers per second, about 19 million miles per hour, your ship carries monstrous kinetic energy on the order of what you'd get from billions of tons of TNT. To settle into a calm orbit around a star or cruise gently near a planet, you have to get rid of almost all of that energy. There is no hidden trick for that. You have to flip the ship so the engines face forward and then burn hard for months at a time. Everything that made your drive dangerous on the way out, radiation, exhaust plumes, waste heat, is now pointed toward your direction of travel, into the thin gas and dust of the Alpha Centauri system. Those deceleration burns heat up your reactors and radiators to their limits. Your forward shields, already worn thin from the interstellar crossing, now sit in the glow of hot exhaust and the plasma created as that exhaust slams into local gas. If your timing is off, you might still be moving too fast when you reach the inner system, and there may not be enough fuel left to fix it. If you try to brake harder to compensate, you risk overloading engines and structure that are already at the end of their design life. You're walking a narrow line between not enough braking and braking so violently the ship rips itself apart, and that whole plan assumes you know exactly where and how to brake. Do you? Our maps of Alpha Centauri are basic compared to our maps of the solar system. You know the main stars, you might know a few planets, maybe some larger belts of asteroids or dust, but you do not launch with a perfect three-dimensional chart of every rock and cloud of gas out there. Over decades of travel, those bodies also move, and your knowledge ages. To hit the right arrival corridor, you have to predict where the stars and planets will be many years in advance, and adjust that prediction with limited delayed data as you get closer. At high approach speeds, even low compared to your cruise, a small navigation error is brutal. A tiny angle mistake when you start your main braking burn becomes a huge positional error millions of kilometers later. You might aim for a clean, low-density path into the inner system, and instead plough through a denser band of dust or gas just when your ship is hottest, most stressed, and least able to shrug off extra hits. If you turn late or burn for too long, you can end up on a trajectory that misses your target entirely, dropping you into a long, useless orbit or sending you past the stars on a path you no longer have fuel to correct. Even the stars you're heading toward are not gentle backdrops, they each bring their own hostile environment. Alpha Centauri. A and B are broadly similar to our Sun, but each has its own magnetic field, solar wind, and cycle of flares. The boundaries between their stellar winds and the local interstellar medium form new shock regions you have never flown through before. Proxima Centauri, the smaller companion, is a red dwarf that is notorious for violent flares and X-ray bursts, far more intense relative to its size than what we get from the Sun. If your mission profile includes a close pass by Proxima to grab a gravity assist or explore one of its planets, you could be diving into space weather that makes the storms near Earth look tame. Out there, you no longer have the Sun's heliosphere as a familiar context. You have shifting, overlapping magnetic bubbles from 3 different stars. Your shielding, tuned for the radiation spectrum you expected during cruise, now has to handle new particle energies and directions. Get your trajectory wrong and you might route the ship right through a region with extreme particle flux, just when your systems are straining with deceleration heat. All of that still assumes your main engines can answer the call one more time, can they? By the time you reach Alpha Centauri, your reactors and drives have been running on and off for decades. They have been repaired, patched and retuned countless times. Components have aged under radiation, thermal cycling, vibration, and mechanical stress. Now you are about to ask those same systems to deliver their longest, most precise, most powerful sustained burn since launch, to bleed off nearly all of your speed. If a major component cracks now, a nozzle throat, a thrust frame, a main feed line, the engine might fail asymmetrically. Thrust from one side drops while the other side keeps firing and the ship starts to tumble. If control systems can't compensate fast enough, G-load spikes sideways, structures see forces they were never meant to take, and the hull can literally twist until it breaks. If the drive has to be shut down entirely to prevent a total breakup, you might be left still moving too fast to stay in the system. You would just sail right past Alpha Centauri on an escape trajectory, with no realistic way to turn around ever. Even if the thrust stays symmetric, an internal failure in the reactor shielding or exhaust handling could suddenly flood parts of the ship with radiation. A slight misalignment of the shadow shield that protected the crew from the reactor for 40 years might suddenly expose living areas to a direct line of sight. Under a long braking burn, that means years worth of radiation dose delivered in a short window, right when the crew needs to be at peak performance to manage arrival. There is no safe backup if the main drive or shielding fails at this stage. You either decelerate correctly, or you're done. Say the big burn works, the engines hold, you slow down to a comfortable fraction of the local orbital speeds, and you drift into the inner system. Are you safe now? If your plan includes landing on a planet, the hardest minutes are still ahead of you. Entering an atmosphere from orbit on Earth already requires tight control of speed, angle, and orientation. Too steep and you burn up, too shallow and you skip back out into space. That is with fresh hardware, short missions, and full support from ground control. On your interstellar mission, your landers and entry vehicles are old by any normal standard. Their heat shields have aged, their structural materials have seen decades of radiation and micro-impacts. Their parachutes and deployment mechanisms have been sitting packed and unused for years. Guidance software will be based on planetary data that might be incomplete or out of date. Atmospheric density, weather patterns, even the exact rotation and shape of the planet could all differ slightly from the models used to design the entry. Small errors in those models translate into different heating profiles and different deceleration patterns. You rely on sensors, altimeters, and onboard computers that may be running patched code and working around failed components to thread a tiny path through a violent high-energy descent corridor. In those last 10 minutes, every part has to work. The heat shield has to hold without unexpected weak spots. The attitude control system has to keep the vehicle at exactly the right angle. Parachutes or retro rockets have to deploy at the correct altitudes and speeds. A stuck valve, a delayed sensor reading, or a misfired thruster can send you from safe landing to total loss faster than anyone on the ground could even finish a status call. It is entirely possible to survive 4 decades in deep space and then die because a decades-old deployment spring snaps, or because the atmosphere you're entering is a bit denser than predicted. So after everything you've passed, vacuum, acceleration, engine radiation, microgravity, storms, cosmic rays, dust, gas, structural decay, psychology, ecosystem risk, and the slow grind of time, the final test can still be the most unforgiving, turning all that survival into a narrow one-shot challenge to arrive in one piece. This video is for educational or entertainment purposes only, and information provided in this video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.